Imagine standing at the outer edge of our solar system, not at Pluto, not even at the distant Oort Cloud, but at an invisible frontier where the sun's breath finally surrenders to the darkness between stars. And beyond this boundary, something extraordinary happens. Behind our moving solar system, stretched across a distance possibly greater than the width of 1,000 planetary orbits, trails an invisible wake. A ghostly current of magnetized plasma carved through the galaxy as the sun barrels through interstellar space at over 50,000 miles per hour. Scientists still argue about its true shape. Is it a comet's flowing streamer? A twisted croissant? A pair of hidden lobes? Tonight we're going to unravel one of the most misunderstood structures in all of astronomy, the heliosphere itself. Before we go any further, if you find these deep dives into the hidden architecture of the cosmos interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Somewhere above your head, right now, an invisible ocean is flowing. You cannot see it. You cannot feel it. No instrument on Earth's surface will ever detect it directly. And yet, everything you have ever known, every sunrise, every eclipse, every planet in the night sky, every spacecraft humanity has ever launched, exists inside this ocean. It is not made of water. It's not made of air. It's made of something stranger, something wilder, something that pours out of our sun at more than 1 million miles per hour and stretches so far into the darkness that our fastest spacecraft, after nearly 50 years of continuous travel, have only just barely begun to reach its outer edge. Astronomers call this ocean the Heliosphere. And to truly appreciate what it is, we have to start not with distant frontiers or exotic physics, but with something as familiar as the sun itself. Now, when you look up at the sun on a bright afternoon, you are looking at a ball of plasma about 865,000 miles across, glowing at a surface temperature of roughly 10,000 degrees Fahrenheit. That much is common knowledge. But the sun does not simply sit there emitting light. It leaks. It bleeds particles into space, continuously, constantly, without pause. And it has been doing so for more than 4.5 billion years. Every single second of every single day, our star releases somewhere close to 1 million tons of its own substance into the vacuum around it. That substance is what scientists call the solar wind, and it is one of the most misunderstood phenomena in all of astronomy. To understand the solar wind, we have to look at a specific layer of the sun called the corona. Now, the corona is the sun's outermost atmosphere, an incredibly hot, incredibly tenuous halo of plasma that surrounds the visible surface. And here is one of the great puzzles of solar physics. The surface of the sun sits at around 10,000 degrees Fahrenheit, but the corona, which is farther from the sun's core, is somehow hundreds of times hotter, reaching temperatures of 1 million to 3 million degrees. Nobody expected that. Everything in nature tends to cool as you move away from a heat source. Your fireplace is hottest at the flame and cooler at the edges of the room. But the sun does the opposite. Scientists have been trying to solve this puzzle for more than 80 years. The problem was first identified in the 1930s, when spectroscopic observations revealed the presence of highly ionized iron in the corona, which is only possible at temperatures of 1 million degrees or more. At first, astronomers thought there must be an error in the measurements. It made no physical sense. Heat should not spontaneously flow from a cooler surface to a hotter atmosphere above it. That would violate the second law of thermodynamics. Something else had to be delivering energy to the corona, some mechanism that bypassed the normal transfer of heat by radiation and convection. Today, two leading theories are competing to explain what that mechanism is. The first involves magnetic waves, specifically what physicists call Alfvén waves, which are oscillations in the magnetic field that carry energy along the field lines and can dump that energy into the corona when they encounter the right conditions. The second involves nanoflares, incredibly small magnetic reconnection events happening constantly across the sun's surface, each one too tiny to see individually, but adding up in aggregate to enormous energy release. The Parker Solar Probe, currently the closest human-made object to ever approach the sun, was designed in part to help distinguish between these possibilities. Its measurements are ongoing, and the answer may become clear within the next decade. But regardless of which mechanism ultimately wins the debate, the consequence for us is the same. The corona is so hot that the sun's own gravity cannot hold onto it. The particles in that superheated outer atmosphere move too fast to stay bound to our star. And so, particle by particle, the sun evaporates outward into space. This is where the solar wind is born. Now, we need to be precise about what the solar wind actually consists of, because the word wind is misleading. It is not moving air. It is not weather in any sense we would recognize. What we call the solar wind is a plasma of charged particles, roughly 96% protons and electrons in nearly equal numbers, with the remaining 4% made up of heavier ions, mostly helium, along with trace amounts of oxygen, carbon, and iron. These particles carry electric charge, which means they respond to magnetic fields in ways that ordinary neutral gases do not. And that is what makes the solar wind so different from anything in our terrestrial experience. There are actually two distinct flavors of solar wind, and both flow from the sun continuously. The slow solar wind comes primarily from the sun's equatorial regions and travels at roughly 800,000 miles per hour when it reaches the vicinity of Earth. The fast solar wind emerges from regions near the sun's poles called coronal holes, dark patches where the magnetic field opens up into space and allows plasma to escape unimpeded. This fast wind can move at up to 1.5 million miles per hour, nearly twice the speed of its slower counterpart. Both winds mix and interact as they expand outward, creating a complex, turbulent flow throughout the solar system. To understand just how sparse this wind is, consider that near Earth, the solar wind contains about 5 to 10 particles per cubic centimeter. Compare that to the air you're breathing right now, which packs about 25 billion molecules into the same volume. The solar wind is millions of times more rarefied than the best vacuum any laboratory on Earth can produce. It is, in every meaningful sense, a hurricane made of almost nothing. And yet, because it fills such enormous volumes of space and moves at such incredible speeds, it carries a tremendous amount of momentum outward from the sun, enough to push back against the pressure of the surrounding galaxy and carve out a bubble of solar influence across billions of miles. Now, we need to talk about what the solar wind actually is on a deeper level, because the word plasma gets used a lot in astronomy and rarely properly explained. Matter in our everyday experience comes in 3 states: solid, liquid, and gas. But there is a 4th state, and it is by far the most common state of matter in the universe. Plasma is what you get when you heat a gas so hot that its atoms come apart. The electrons get stripped from the nuclei, and instead of a collection of neutral atoms bouncing around, You have a soup of positively charged nuclei and negatively charged electrons, all moving freely, all electrically active. Plasma behaves nothing like an ordinary gas. Because its particles carry electric charge, they respond powerfully to magnetic fields. They spiral around field lines, they get deflected by them. They can carry electric currents. They can generate their own magnetic fields through their motion. And crucially, plasma and magnetic fields become locked together in a phenomenon that physicists call frozen-in flux. Wherever the plasma flows, the magnetic field is carried along with it. Wherever the magnetic field goes, the plasma must follow. This locking together of plasma and magnetic field lines has consequences that reach all the way across our solar system. When the sun releases a burst of plasma from a coronal mass ejection, it releases a magnetic field along with it. When a solar flare hurls particles outward, those particles carry magnetic structure with them. Even the quiet, steady solar wind flowing outward at all times is dragging the sun's magnetic field along with it, unspooling it into space like thread pulled from a spinning reel. Nothing about the solar wind can be understood without also understanding the magnetism it carries. Now, imagine what this means for the space around the sun. As the sun rotates on its axis, it does so with a period of roughly 27 days at its equator, though slower nearer the poles. This is called differential rotation, and it is one of the strangest properties of our star. Unlike a solid ball that would spin uniformly, the sun's fluid nature allows different latitudes to rotate at different rates. The equatorial regions complete a rotation every 25 days or so, while regions near the poles take closer to 35 days. This differential rotation is thought to be one of the drivers behind the sun's magnetic dynamo, the process that generates the enormous magnetic field we have been discussing. But regardless of exactly how the sun rotates, the fact that it rotates at all has profound consequences for the shape of the solar wind and its embedded magnetic field. Consider a specific point on the sun, releasing solar wind outward. As that solar wind travels outward, the source point on the sun keeps rotating. So the next puff of solar wind from that same point is released at a slightly different angular position, and the puff after that at a slightly different angle again. The result is that the trail of solar wind coming from any given point on the sun does not go straight outward. It curves, forming a spiral pattern in space. The classic analogy for this is a lawn sprinkler that rotates as it sprays water. The individual water droplets travel outward in straight lines from the sprinkler head. But because the head is rotating, the pattern of droplets in the air forms a curving spiral, not straight radial lines. Now imagine this happening not with water droplets, but with charged plasma, dragging a magnetic field with it. And you have a picture of what happens in the solar wind. The magnetic field lines carried by the solar wind get wound into an enormous spiral pattern that fills the entire volume of the solar system. There is one important refinement to this picture. The spiral shape depends on how fast the solar wind is moving. Fast solar wind, which travels at over 1 million miles per hour, produces a more tightly wound spiral because the wind gets farther from the sun before the rotation can twist it much. Slow solar wind, moving at 800,000 miles per hour, produces a more loosely wound spiral because the rotation has more time to twist it. This means that the actual magnetic field structure in space is not one simple spiral, but a complex pattern with fast and slow components interleaved in ways that depend on where you are in the solar system. Near Earth, at 1 astronomical unit from the Sun, the average angle of the magnetic field to the line pointing back at the Sun is about 45 degrees. That is the classic Parker spiral angle at our distance. Farther out, at the orbit of Jupiter, the angle is closer to 80 degrees, meaning the magnetic field is almost perpendicular to the direction pointing back at the Sun. By the time you reach the outer solar system, the magnetic field is nearly circling the Sun rather than pointing away from it. And in the far reaches of the heliosphere, out near the termination shock, the field is wound so tightly around the Sun that it becomes almost a series of concentric rings. This spiral structure fills every corner of the solar system. Every planet orbits inside it, every spacecraft passes through it, every particle of solar wind that reaches Earth has traveled along its curving path, carrying with it the frozen-in magnetic field that binds it inseparably to our star. This structure has a name. It is called the Parker spiral, after the American physicist Eugene Parker, who predicted its existence in 1958, when almost nobody else believed the solar wind was even real. Parker's idea was radical at the time. He argued that the Sun must be continuously blowing off its atmosphere, that this outflow must be supersonic, and that as it expanded, it must carry the Sun's magnetic field into a rotating spiral shape. Other scientists ridiculed the paper. Reviewers rejected it. One reviewer told Parker to go to the library and educate himself before submitting again. But Parker held his ground, and within a few years, direct observations from early space probes confirmed everything he had predicted. The solar wind was real. It was supersonic, and it was carrying the Sun's magnetic field into a spiral pattern exactly as he had described. Today, the Parker spiral is one of the fundamental structures in our understanding of the solar system, and NASA named its groundbreaking mission to the Sun's corona in his honor. Eugene Parker himself lived long enough to see that spacecraft launch in 2018, becoming the first person in history to witness a mission named after him take flight to its target. So, we now have a picture. A blazing sun continuously exhaling a supersonic stream of charged plasma in every direction, dragging its magnetic field outward, twisted by rotation into a vast spiral that fills the space around all of the planets. This exhaled plasma pushes outward relentlessly, carving out a region of space where the sun's influence is dominant. And this region, this vast domain shaped by the sun's own outflow, is the heliosphere. Now, here is the first thing you must understand about the heliosphere. It is not a solid bubble. It is not a shell. It is not a wall you could bump against. If you were somehow able to travel out to the edge of the heliosphere, you would not encounter any kind of surface, any kind of membrane, any physical barrier. What you would encounter is a change in the density of the plasma around you, a change in the direction of the magnetic field, a change in the composition of the particles zipping past your spacecraft. The heliosphere is a region, not an object. It is defined by what fills it, not by any structure that contains it. And what fills it is the solar wind and the magnetic field that comes with it, all the way out to the point where those things can no longer push back against the material of the galaxy beyond. That distinction, region versus object, matters enormously. Because when most people imagine the solar system, they imagine a series of planets orbiting a central star, and they imagine an edge somewhere out there beyond Pluto where the whole thing stops. But that mental picture is deeply misleading. There is no single edge of the solar system. There are several possible edges, and they all sit at wildly different distances, and they all mean something different depending on which force you happen to be paying attention to. Let me walk you through this carefully, because it is one of the most beautiful pieces of confusion in modern astronomy. If you ask what is the edge of the planetary solar system, meaning the region where the classical planets orbit, then your answer is around Neptune, at roughly 30 astronomical units from the Sun. An astronomical unit, remember, is the distance from Earth to the Sun, about 93 million miles. So the planetary edge sits about 30 times that distance out. It is, in cosmic terms, extraordinarily close to home. All 8 planets, from Mercury to Neptune, fit into that inner sanctum. But if you ask instead, what is the edge of the region shaped by the solar wind, then your answer is very different. That edge, the outer boundary of the heliosphere, sits somewhere around 120 astronomical units from the Sun in the direction our star is moving, and possibly much farther in the opposite direction. So the heliosphere is roughly 4 times wider than the planetary system in one direction, and possibly far more than that in another. And it stops at the boundary called the heliopause, where the pressure of the Sun's outward wind finally equals the pressure of the surrounding galaxy pushing back. But we're still not done, because the Sun's gravitational influence extends far, far beyond the heliopause. Gravity, unlike the solar wind, does not need a physical medium to travel through. It reaches out silently, invisibly, weakening with distance but never stopping. And there is a vast, distant reservoir of icy bodies, comets, small worlds, gravitationally bound to the Sun that sits so far outside the heliosphere that it barely feels the Sun's warmth at all. This reservoir is called the Oort Cloud, and it is thought to begin at somewhere around 2,000 astronomical units from the Sun and extend outward to perhaps 100,000 astronomical units. That is nearly halfway to the nearest star system. And every one of those distant icy bodies is still, technically, part of the solar system, because the Sun's gravity still holds them in loose, extraordinarily long orbits. So think about what this means. If you took a spacecraft and traveled outward from the Sun, you would pass Neptune and leave the planetary region behind fairly early. You would then travel for a very long time through the outer heliosphere before finally crossing the heliopause and leaving the solar wind's domain behind. And even then, even after crossing what many people casually call the edge of the solar system, you would still be moving through a region completely dominated by the Sun's gravity, populated by billions of icy bodies that still orbit our star, for another distance many times larger than everything you had already crossed. The Oort Cloud sits mostly outside the heliopause, in what is technically interstellar space in terms of plasma physics, but which is still very much part of the Sun's gravitational family. Those two boundaries, the plasma edge and the gravitational edge, do not agree with each other at all. They differ by roughly a factor of 1,000. This is why there is no single, universally correct answer to the question of where the solar system ends. It depends entirely on what you mean. Do you mean where the planets stop orbiting? Then the edge is near Neptune. Do you mean where the Sun's outflowing wind stops pushing back on the galaxy? Then the edge is at the heliopause, 4 times farther out. Do you mean where the Sun's gravity finally becomes negligible compared to other stars? Then the edge is 1,000 times farther still, at the outer reaches of the Oort Cloud. Every one of these boundaries is real. Every one of them means something, and every one of them sits at a different distance. The heliosphere, then, is a specific one of these boundaries. It is the region of space where the sun's plasma and magnetic field dominate. It is the bubble, if you can call it that, carved out by our star's continuous exhalation into the galaxy, and its scale is genuinely difficult to comprehend. Consider this. Voyager 1, launched in 1977, is the fastest human-made object ever to leave the inner solar system. It has been traveling outward, without stopping, without slowing down, for close to 5 decades. It moves at about 38,000 miles per hour, roughly 17 kilometers per second, relative to the sun. And even after all of that time, all of that constant velocity, all of those hundreds of billions of miles behind it, Voyager 1 only crossed the outer boundary of the heliosphere in 2012. It took 35 years of unrelenting outward motion for a spacecraft moving at incredible speeds to cover the distance from Earth to the edge of the sun's plasma domain. And when it finally crossed that boundary, it did not exit the solar system in any meaningful sense. It simply exited the bubble of solar wind. The sun's gravity still holds it. The Oort Cloud still lies far ahead if Voyager 1 were headed in that direction, which it is not exactly. There are still billions of icy bodies bound to the sun beyond where Voyager sits right now. This scale is difficult even for professional astronomers to internalize. The heliosphere is a structure so large that our fastest spacecraft need decades to cross it. It contains everything we normally think of as our home, every planet, every moon, every asteroid, every human being who has ever lived, every civilization that has ever risen or fallen, every act of art or science or love, all of it has happened inside this bubble of plasma. And the bubble itself is created by a star continuously breathing outward into a much larger, much colder, much stranger environment surrounding it. Now, one more thing before we press outward toward those distant boundaries. The heliosphere is not the same as the sun's atmosphere. The corona ends fairly close to the sun, within a few solar radii of the surface. What extends outward beyond that is not properly the sun's atmosphere anymore. It is the solar wind, an outflow rather than an envelope. Similarly, the heliosphere is not the same as the sun's gravitational influence, which we have just discussed. And it is not the same as the light of the sun, which streams outward independently of the plasma and reaches distances vastly greater than the heliopause. What the heliosphere specifically represents is the domain of the sun's magnetized wind. Nothing more, nothing less. It is the region where the solar wind dominates, where the sun's magnetic field structure fills space, where charged particles originating in our star still outnumber those coming from elsewhere in the galaxy. And what surrounds this domain is not empty space. That is a crucial point, and one that popular science often glosses over. Between the heliosphere and the nearest stars sits a region called the local interstellar medium. It contains diffuse gas, thin plasma, tiny grains of dust, a weak but persistent magnetic field of its own, and energetic particles called galactic cosmic rays that come from ancient stellar explosions across the Milky Way. This local interstellar medium is not much in terms of density. If you scooped up a cubic centimeter of it, you might find only a fraction of a particle on average. But it is there. It is real, and it pushes back against the solar wind everywhere the two meet. That, in the simplest possible terms, is the story of the heliosphere, a star continuously exhaling plasma outward. That plasma dragging the sun's magnetic field into a spiral pattern across enormous distances. Interstellar material pushing back against the plasma from every side. And somewhere between the two, a boundary where the pressures balance, where the sun's influence gives way to the galaxy's influence, where our home ends and the wider Milky Way begins. Everything else, every strange feature we are about to explore, every boundary layer, every shock front, every enormous downstream tail follows from this simple and constant exhalation. The sun breathes, the galaxy pushes back, and in between, our world is held inside an invisible bubble whose true shape and scale we are only just beginning to understand. To understand what happens behind the heliosphere, you have to first understand something about the sun itself that most people never think about. Our star is moving. It is not sitting still in the middle of the galaxy, waiting for the planets to orbit around it. The sun is barreling through the Milky Way at roughly 143 miles per second, or about 500,000 miles per hour, on a long, slow orbit around the galactic center that takes some 225 million years to complete. But that galactic orbit is not what matters for the heliosphere. What matters for the heliosphere is the sun's motion relative to the material immediately surrounding it, the local interstellar medium through which our star is currently passing. And that motion, measured in the reference frame of the local gas around us, comes out to about 52,000 miles per hour. 52,000 miles per hour is genuinely fast by human standards. If you could somehow throw a stone at that velocity, it would cross the entire United States in less than 3 minutes. But in the context of the galaxy, it is a relatively gentle drift. And it is this drift, this constant motion of the sun through the surrounding interstellar gas, that gives the heliosphere its distinctive shape. Think of it this way. If the sun was sitting perfectly still relative to the material around it, the heliosphere would be a fairly symmetric object, roughly spherical, expanding outward equally in every direction until the pressure of the interstellar medium eventually stopped it. But because the sun is moving, that symmetry breaks. On the side of the heliosphere that faces the sun's direction of motion, the upstream side, the interstellar medium, is being pushed harder. It compresses, it piles up. The heliosphere on that side is squeezed inward, forced closer to the sun than it would otherwise be. And on the opposite side, the downstream side, the interstellar medium slides away as the sun moves forward, leaving room for the heliosphere to expand, or to stretch, or to trail. And it is this trailing region, this downstream extension of solar plasma and magnetic field behind the moving sun, that scientists call the heliotail. Now, when you first hear that the heliosphere has a tail, your instinct is probably to picture something like a comet. A bright, focused, streaming plume of gas trailing behind a moving object. This is the mental image that has appeared in countless textbook illustrations and popular science articles for decades. In this classical picture, the heliosphere looks a lot like a raindrop or a comet, with a rounded, compressed nose at the upstream side and a long, tapering tail extending behind. It is a beautiful, intuitive picture. It is easy to draw, it is easy to remember, and for a long time, it was the default way scientists depicted the shape of our home in the galaxy. But that picture may be seriously incomplete, or perhaps even wrong in significant ways. And that is one of the most exciting stories in modern heliophysics. Let us start with what everyone agrees on. There is a downstream region of the heliosphere. The sun is moving through the interstellar medium, so material that used to be part of the heliosphere upstream, on the leading side, gets left behind on the trailing side as the sun moves forward. This means that behind the sun's direction of motion, there is a region of space filled with solar plasma, threaded with the sun's magnetic field that extends outward for some distance before it finally mixes with and gets overwhelmed by the surrounding interstellar medium. That much is uncontroversial. Something exists downstream, and it has to be extended in the direction opposite to the sun's motion, simply because that is the geometry of the situation. What is controversial is everything else. How long is this downstream region? Where does it end? Is it a smooth, tapering tail like a comet? Or is it something much more complicated? Does the sun's magnetic field carve the downstream region into separate lobes or channels? Is the heliosphere shaped like a raindrop, like a croissant, like a bullet, like some entirely other geometry we do not yet have a good name for? These are the questions that keep heliophysicists arguing at conferences, publishing competing models, and reanalyzing every scrap of data they can get their hands on. The reason this debate exists is that we cannot see the heliotail directly. We cannot photograph it. We cannot fly a spacecraft through it, not for many decades at least. Voyager 1 is heading roughly upstream into the direction the sun is moving. Voyager 2 is heading roughly sideways. Neither one is going to travel down the length of the tail anytime soon. So everything we know about the heliotail, everything at all, has to come from indirect observations, computer models, and one very special kind of measurement that has revolutionized this entire field: energetic neutral atoms. Energetic neutral atoms are so important to modern heliophysics that they deserve a careful explanation. Here is what they are. In the plasma of the outer heliosphere, especially in the Helios heath, you have two populations of particles mixed together. Charged particles, which are protons, electrons, and heavier ions moving fast and interacting with the magnetic field. And neutral atoms, mostly hydrogen and helium, that have drifted in from the surrounding interstellar medium. Sometimes, a fast-charged particle and a slow neutral atom collide, and an electron jumps from the neutral atom to the charged particle. In an instant, their roles reverse. The formerly charged particle becomes a fast neutral atom, retaining its enormous speed, and the formerly neutral atom becomes a slow, charged particle, joining the local plasma. Now here is what makes this process so scientifically valuable. That fast neutral atom, moving at hundreds of miles per second, is no longer affected by magnetic fields. It travels in a straight line. It does not curve. It does not spiral. It just goes. And it keeps going, undisturbed, until something absorbs it or measures it. This means that if a fast neutral atom is created somewhere out in the Helios sheath, out near the heliopause, it can travel in a straight line all the way back toward the inner solar system, where an instrument can detect it. And by measuring the direction it came from and its energy, that instrument can effectively look outward to the region where the atom was created. Energetic neutral atoms let us see distant regions of the heliosphere that no spacecraft will ever visit. This is the principle behind a NASA mission called the Interstellar Boundary Explorer, or IBEX. IBEX launched in 2008, and it has been slowly and carefully mapping the sky, measuring energetic neutral atoms coming from every direction, building up an all-sky picture of what the outer heliosphere looks like, based on the flux of these ghost particles. And what IBEX found completely changed how scientists think about the heliosphere. The first major discovery, announced in 2009, was something no one had predicted. When IBEX put together its first all-sky map of energetic neutral atoms, a strange feature appeared. There was a bright, narrow ribbon of enhanced emission stretched across the sky. It was not diffuse. It was not evenly distributed. It was a distinct, coherent, arc-shaped band of energetic neutral atoms that ran across the map like a cosmic ring. This became known as the IBEX Ribbon, and its origin has been the subject of intense investigation ever since. Nobody predicted the ribbon before it was discovered. Every model of the outer heliosphere had assumed that energetic neutral atom emission would be relatively smooth, gradually varying across the sky, with maybe some broad features corresponding to the general geometry of the heliosphere's shape. Instead, IBEX found this astonishing, sharp, ordered structure. And within days of its announcement, the theoretical papers started pouring in. Every heliophysicist with a computer wanted to explain what the ribbon was. Different explanations were proposed, and many of them are still competing with one another today. One of the leading explanations is that the ribbon marks the region where the sun's magnetic field, as carried outward by the solar wind and deformed by the interstellar environment, happens to lie perpendicular to the local interstellar magnetic field just outside the heliopause. In directions where these two fields are perpendicular, energetic particles behave in a special way that it increases the production of neutral atoms detectable back at Earth. In other directions, the geometry is different and the emission is weaker. If this explanation is right, then the IBEX ribbon is essentially a picture of the geometry of the interstellar magnetic field around our solar system. It is a way to see the invisible shape of the galaxy's magnetic environment just beyond our heliosphere. Other explanations have been proposed as well. Some involve reflected solar wind protons. Others involve compressed regions of the outer heliosheath. Others involve interactions between the interstellar and solar magnetic fields that are more complex than the perpendicular field picture. Debate continues. What is not in doubt is that the IBEX ribbon exists, that it is one of the most striking features ever discovered in the outer heliosphere, and that it tells us something important about how solar and interstellar plasma interact at the boundary. Now, IBEX also made another major discovery, one that goes right to the heart of the shape debate. When scientists looked at the pattern of energetic neutral atoms coming from the downstream direction, from the region where the heliotail should be, they didn't see what the classical comet-shaped picture predicted. They did not see a single narrow, focused tail. Instead, they saw something more complicated. The emission from the tail region appeared to have structure. It looked like it might be divided into distinct lobes. There seemed to be two brighter regions, sometimes described as tail lobes, separated by a fainter region between them. These lobes seemed to be aligned in a particular way with the sun's magnetic equator, suggesting they were shaped by the interaction between the sun's magnetic field and the interstellar environment. This discovery led some scientists to propose an entirely different shape for the heliosphere. Instead of a long, comet-like tail extending far downstream, they suggested the heliosphere might have a much more compact shape, with the downstream region divided into two curved lobes that wrap around and possibly join back with the upstream side. In some models, the heliosphere looks less like a raindrop and more like a croissant, a curved, roughly annular structure with two lobes on the downstream side. This became known informally as the croissant model of the heliosphere. The croissant model is not universally accepted. It is one of several competing pictures. Other scientists, using different datasets, different models, And different assumptions about the interstellar magnetic field argue that the heliosphere still has a substantial tail extending downstream, perhaps for hundreds or even thousands of astronomical units. In their view, the lobes seen in IBEX data are features of the tail rather than evidence against a tail. The bulk plasma flow may extend far downstream, even if the energetic neutral atom emission does not remain bright at those distances. This debate is genuinely unresolved. When you read about the heliosphere in popular articles, you will often see confident illustrations of one shape or another. Sometimes you will see the classical comet-like picture. Sometimes you will see the croissant model. Sometimes you will see hybrid shapes that combine features of both. But the honest scientific answer is that we do not yet know the exact three-dimensional shape of the heliosphere. Different models and different observations give different answers, and reconciling them all into one coherent picture remains one of the great open problems in heliophysics. What everyone agrees on is that there is downstream extension, some kind of trailing structure that follows the sun as it moves through the galaxy. What everyone agrees on is that the sun's magnetic field organizes this downstream region in ways that produce structure. Whether that structure is best described as a tail with substructure, or as lobes, or as a croissant, or as something we do not yet have a good name for. What everyone agrees on is that the exact length of the heliotail, in the sense of how far downstream you have to travel before you can no longer identify solar plasma against the interstellar background, is genuinely unknown. The classical estimates suggested the heliotail might extend for thousands of astronomical units, tens of billions of miles, possibly reaching a length of hundreds or even thousands of times the distance from Earth to the Sun. In some of the more dramatic older illustrations, the heliotail is drawn as extending for so much distance that it dwarfs everything else in the picture. The more recent models, especially those informed by IBEX data, tend to favor shorter estimates. Some of them place the effective length of the downstream region at a few hundred astronomical units at most, comparable to the size of the upstream heliosphere rather than dramatically longer. Which of these estimates is closer to reality remains an open question. To make matters more complicated, the shape of the heliotail almost certainly changes with the solar cycle. The sun goes through an approximately 11-year cycle of magnetic activity, transitioning from a quiet phase called solar minimum to a highly active phase called solar maximum, and back again. During solar maximum, the sun releases stronger solar wind, produces more coronal mass ejections, and has a more chaotic magnetic field. During solar minimum, the wind is gentler and the field is more organized. The heliosphere responds to these changes. It breathes in and out. The termination shock moves closer and farther. The pressure at the heliopause rises and falls, and downstream, the heliotail responds too. Its structure changes. Its magnetic organization shifts. Its brightness in energetic neutral atoms fluctuates. This means that even if we could nail down the exact shape of the heliotail at one particular moment, it would not be the same shape a decade later. The heliotail is a dynamic object. It has weather. It has seasons of a kind, driven by the 11-year rhythm of solar activity. Trying to describe its exact geometry is a little like trying to describe the exact shape of a plume of smoke rising from a fire in variable wind. You can describe general patterns, average behavior, characteristic features, but the specific instantaneous shape at any given moment is always in flux. There is one more feature of the downstream region that deserves attention, and that is the role of the sun's magnetic field in dividing the tail into distinct structures. The Sun's magnetic field has an alternating polarity, meaning that different regions of the field point in opposite directions. As the solar wind carries this field outward, the boundary between opposite polarities gets carried outward too, forming an enormous, wavy, rotating structure called the heliospheric current sheet. This current sheet is thin in the direction perpendicular to itself, but it stretches across essentially the entire heliosphere, and it separates regions where the magnetic field points one direction from regions where it points the opposite direction. When you follow the current sheet outward into the downstream region, all the way into the heliotail, its geometry becomes an important part of the tail's structure. The current sheet divides the tail into sectors. On one side of the sheet, the magnetic field points one way. On the other side, it points the other way. Where the two sides meet, magnetic reconnection can occur, releasing energy and rearranging the field. This means the heliotail is not one uniform structure. It has magnetic subdivisions, magnetic geometry that varies from place to place, driven by the Sun's fundamental magnetic polarity structure and modulated by the solar cycle. To really appreciate what the heliospheric current sheet is, you have to picture something genuinely strange. Imagine a wavy, rippling surface like the brim of an enormous cosmic hat, extending outward from the Sun's equator in every direction. This surface is where the magnetic field carried by the solar wind changes direction. Above it, the field points one way. Below it, the field points the other way. And as the Sun rotates, this wavy surface rotates with it, sweeping through space like a slowly rotating dancer's skirt. In 3 dimensions, the current sheet looks a little like a ballerina's skirt, tilted from the Sun's rotational axis, undulating up and down as it spins. The tilt of the current sheet varies with the solar cycle. During solar minimum, the sheet is relatively flat, closer to the Sun's equatorial plane. During solar maximum, when the Sun's magnetic field is more chaotic, the sheet becomes highly warped, extending far above and below the equator, sometimes twisting into shapes that no simple geometry can describe. The current sheet fills the entire heliosphere. Every planet, including Earth, crosses the current sheet multiple times per rotation of the Sun, sometimes finding itself in a region of one magnetic polarity, sometimes finding itself in a region of the opposite polarity. When Earth is in what scientists call a positive polarity sector, the Sun's magnetic field near our planet points generally outward from the Sun. In a negative sector, it points inward. These sectors have real consequences for the way solar wind interacts with Earth's magnetosphere, and they affect everything from auroral activity to the intensity of certain kinds of cosmic ray fluctuations at ground level. And this current sheet does not stop at Neptune. It does not stop at Pluto. It extends all the way outward through the heliosphere, into the Helios Heath, into the downstream tail regions. Its structure at those enormous distances is one of the most difficult things to model, because the sheet's original geometry near the Sun gets distorted by all of the plasma physics we have been discussing. In the tail, the current sheet may be stretched, folded, torn apart by reconnection, or organized into complex sector structures that scientists are still working to understand. Now, one thing worth appreciating about the shape debate is just how the competing models are actually built. Scientists do not simply guess. They combine everything they have. They start with the Voyager measurements, which give them a small number of direct data points at the boundaries. They add IBEX energetic neutral atom maps, which give them a global picture at lower resolution. They include measurements of the interstellar gas flowing into the solar system, which reveals the direction and speed of the surrounding galactic environment. They incorporate solar wind measurements from spacecraft like the Parker Solar Probe and dozens of other missions, which tell them what is being sent outward from the sun in real time. And then they feed all of that into enormous computer simulations that try to solve the equations of magnetohydrodynamics, the physics of how magnetized plasmas move across the entire volume of the heliosphere. These simulations run on supercomputers for weeks or months at a time. Different research groups use different assumptions, different numerical methods, different levels of detail, and they get somewhat different answers. That is why the shape debate persists. It is not that scientists are being careless, it is that we are trying to model an enormous, complicated, three-dimensional structure with limited direct measurements, and the answers depend sensitively on choices that are themselves still being refined. One particularly fascinating aspect of these simulations is that they occasionally predict features that observers then go looking for and actually find. Several years ago, models predicted that the heliosphere should have a specific asymmetric distortion caused by the interstellar magnetic field pushing on one side more than the other. When astronomers went back through IBEX data with this prediction in mind, they found evidence of exactly that asymmetry, a tilted structure in the outer heliosphere that had been sitting in the data all along, but had not been recognized as significant. This kind of interplay between theory and observation is how the field advances. A simulation makes a prediction. Observers hunt for it. If they find it, the model gains credibility. If they do not, the model needs revision. That is science working exactly as it should. This is one of the reasons the heliosphere is such a fascinating subject. It sits at the intersection of nearly every major branch of space physics. Plasma dynamics, magnetohydrodynamics, particle acceleration, radiation transport, atomic physics. All of these disciplines are required to fully describe what happens inside our star's plasma domain. No single specialist can master all of them. Heliophysics has therefore grown into one of the most collaborative fields in modern astronomy, with teams of dozens or sometimes hundreds of scientists working together on individual studies. Each researcher contributes a piece of the puzzle, and the complete picture emerges only from the combination of all their expertise. There is something worth pausing to appreciate here. The sun and its heliosphere are moving through the galaxy at 52,000 miles per hour. But space is so unimaginably vast that this motion is imperceptible on human timescales. The sun does not travel a full astronomical unit relative to the local interstellar medium in less than several months. The heliotail, however long it may actually be, has been forming and reforming for the entire history of our solar system for billions of years, as the sun has wandered through different regions of the local galaxy. Every one of us, every human who has ever lived, has spent our entire existence inside this vast, ever-changing plasma and magnetic field structure whose true shape we cannot even agree on. And the story gets stranger, because as our sun moves through the galaxy, it does not always encounter the same interstellar environment. Sometimes it passes through regions of relatively dense interstellar gas. Sometimes it passes through very rarefied regions. Sometimes it plows into interstellar clouds with different magnetic properties. Right now, the sun is passing through a region called the local interstellar cloud, a wisp of slightly denser than average interstellar gas that our star is thought to have entered somewhere between 40,000 and 150,000 years ago. Before that, the Sun was passing through a different region of the local galactic environment. Before that, another region still. And each of these environments would have produced a somewhat different heliosphere, a somewhat different downstream tail, a somewhat different arrangement of boundaries, which means that the heliosphere as we see it today is not the eternal heliosphere. It is a snapshot. It is the shape our star's plasma domain happens to have because of where the Sun happens to be right now in its long, slow journey around the Milky Way. In another 100,000 years, when the Sun has drifted into a new region of the local galactic environment, the heliosphere will look different. Its upstream nose might be compressed harder or less hard. Its downstream tail might extend further or be truncated closer. Its shape might tilt, warp, elongate, or contract. And all of this happens without any material inside the heliosphere ever noticing, because the changes unfold over timescales far longer than a human lifetime. There is a deep and slightly humbling truth in all of this. The heliosphere is our home. It is the environment inside which every planet, every moon, every asteroid, every human, every civilization has existed for as long as the solar system has existed. And yet, we have only been able to study it in detail for a few decades. Voyager 1's crossing of the heliopause was just over a decade ago. IBEX is still returning data. New missions to study the outer heliosphere are being planned. We are, quite genuinely, in the earliest era of understanding this vast structure that surrounds us. Every decade brings new data, new surprises, new refinements to our picture. The exact shape of the heliotail, the true nature of the IBEX ribbon, the length and structure of the downstream region. All of these are questions we may not fully answer for another generation, perhaps longer. But even without a final settled picture, we can say this. Behind our moving solar system, stretching for some distance we cannot yet exactly measure, there is a downstream region carved out by the Sun's continuous exhalation, structured by its magnetic field, deflected and shaped by the surrounding interstellar environment. It follows us. It streams behind us. It changes with the seasons of the Sun. And it is one of the strangest, most invisible, most influential features of the environment we all live inside. Everything we have described so far, the outward streaming solar wind, the termination shock, the vast heliosheath, the boundary at the heliopause, the enormous downstream tail with all its unresolved geometry, might sound like a fixed structure, a giant plasma bubble sitting in place, changing only where our spacecraft happen to fly through it. But nothing about the heliosphere is fixed. Nothing about it is still. The entire structure, from the innermost regions of the solar wind out to the farthest reaches of the tail, is constantly changing. It breathes, it grows and shrinks, it responds. And to understand why, we have to go back to the source of everything and pay attention to something that our star does that shapes the entire environment we live in. The Sun has a heartbeat. It is a slow heartbeat, roughly 11 years from one pulse to the next, but it is remarkably regular, and it drives an entire rhythm across the solar system. Astronomers call it the solar cycle. Over the course of approximately 11 years, the Sun transitions from a relatively quiet state called solar minimum through a rising phase to a highly active state called solar maximum, and then back down to another minimum. And every 11 years or so, at the peak of maximum, the sun's magnetic field does something extraordinary. It flips. The north magnetic pole becomes the south, and the south becomes the north. It is not a subtle change. It is a fundamental reorganization of the sun's magnetic character, and it happens every solar cycle without fail, for as long as anyone has been paying close attention. The solar cycle affects everything about the environment the sun creates around itself. During solar minimum, the sun produces fewer sunspots, fewer flares, fewer coronal mass ejections. The solar wind is generally calmer, though still enormously energetic by any reasonable standard. The sun's magnetic field is more orderly, less chaotic, more easily traced outward through the solar system in the clean spiral pattern first predicted by Eugene Parker. And the pressure that the solar wind exerts on the surrounding interstellar medium is somewhat lower than average. During solar maximum, everything intensifies. Sunspots dot the surface, flares erupt more frequently. Coronal mass ejections, those enormous bubbles of plasma that are hurled outward from the sun's corona during the most violent solar events, occur several times a week rather than a few times a month. The solar wind becomes gustier, more variable, sometimes surging outward at speeds well above its average. The magnetic field carried outward becomes more tangled and complex, and the pressure that the entire solar wind system exerts on its surroundings rises. The heliosphere responds to all of this. Not instantaneously, of course. The solar wind takes months, sometimes years, to travel from the sun to the outer boundary regions. So when the sun becomes more active, that increased pressure does not reach the termination shock immediately. It has to propagate outward at the speed of the solar wind, which is fast, but not infinite. By the time an increase in solar activity actually reaches the termination shock and starts pushing on it, that increase in activity may have already peaked back at the sun. The outer heliosphere is always responding to a somewhat delayed version of what the inner heliosphere was doing many months or years ago. But respond it does. When the solar wind pressure increases, the termination shock gets pushed outward. When the pressure decreases, the shock relaxes back inward. The heliopause responds similarly, though even more slowly, because it is farther out and its motion depends on the balance between the sun's outward pressure and the interstellar medium pushing back. Voyager 1 and Voyager 2, in fact, may have crossed the termination shock at slightly different distances, not just because of the intrinsic asymmetry of the heliosphere, but also because they crossed it at different points in the solar cycle. The shock's location was actually changing during the years between the two crossings. This means the heliosphere is not a static structure, it is a breathing structure. On timescales of years and decades, it expands and contracts. Its boundaries drift inward and outward. Its shape shifts subtly, always dominated by the underlying rhythm of the solar cycle. If you could somehow watch the heliosphere in time-lapse over centuries, you would see it pulsing gently, an enormous plasma organism responding to the mood of its central star. And this breathing has real consequences for what happens inside the heliosphere. Because the heliosphere is not just an interesting piece of astrophysics, it also plays a critical role in one of the most important environmental factors affecting every planet in the solar system. The heliosphere partially shields the inner solar system from galactic cosmic rays. Galactic cosmic rays are among the most energetic particles in the universe. They are mostly protons, though heavier nuclei are also part of the mix, and they travel through the galaxy at velocities approaching the speed of light. They are produced by the most violent events in the Milky Way. Supernova explosions from dying stars, powerful shock waves in the interstellar medium, and interactions with the enormous magnetic fields near active regions across the galaxy. Once produced, they can travel for millions of years, wandering through space, bouncing off magnetic field structures, occasionally passing through our solar system on their way to somewhere else. If galactic cosmic rays reach the inner solar system unimpeded, they would be a serious problem. Their extraordinary energies mean that they can penetrate deep into materials, causing damage to electronic components, contributing to genetic mutations in living tissue, and creating cascades of secondary particles when they interact with atoms in an atmosphere. For any complex biological system, high doses of cosmic radiation are dangerous. For spacecraft electronics, they can cause data errors and even permanent damage. So the question of how much cosmic radiation reaches the inner solar system and how much is blocked or deflected before it gets there matters enormously. The heliosphere is the first line of defense. As galactic cosmic rays approach the outer boundary of the heliosphere, they encounter the sun's magnetic field embedded in the solar wind. Charged particles cannot cross magnetic field lines easily. They spiral around them, they get deflected sideways, they lose energy through various interactions with the plasma. Many of them, especially the lower energy ones, cannot even penetrate to the inner solar system at all. They get turned away at the outer heliosphere and never make it any closer to Earth than the outer boundary of the Helios Heath. But, and this is where you have to be careful, the heliosphere is not a perfect shield. It does not block all galactic cosmic rays. It cannot. The highest energy cosmic rays are simply too energetic to be significantly deflected by the sun's magnetic field. They plow through the heliosphere as if it were barely there, arriving at Earth and other inner solar system objects with much of their original energy intact. And even for lower energy cosmic rays, the shielding is partial. Some of them do make it through, following complicated paths through the heliosphere's magnetic structure, losing some energy along the way, but still arriving in the inner solar system in significant numbers. And here is where the solar cycle comes back in, because the shielding effect of the heliosphere depends on the strength of the solar wind and the sun's magnetic field. And because those things change on an 11-year cycle, the amount of cosmic radiation reaching Earth also varies on an 11-year cycle. During solar maximum, when the sun is more active, the shielding is somewhat stronger, and fewer cosmic rays reach the inner solar system. During solar minimum, when the sun is quieter, the shielding weakens, and more cosmic rays make it through. This effect has been measured for decades. Scientists can watch cosmic ray intensity at Earth rise and fall in the opposite pattern from solar activity. When the sun is quiet, the galaxy shines through more brightly. When the sun is stormy, the galaxy is dimmer in cosmic rays. This has real implications for space exploration. Astronauts traveling beyond low Earth orbit are exposed to significantly more radiation than people on the ground, because Earth's atmosphere and magnetic field provide additional protection that the heliosphere alone does not. But even for spacecraft in interplanetary space, or for future crews traveling to Mars, the radiation environment is not constant. It shifts with the solar cycle. Timing emission for solar maximum reduces cosmic ray exposure, but it increases the risk from solar flares and coronal mass ejections. Timing for solar minimum reduces solar risks, but increases cosmic ray exposure. There is no perfectly safe time to travel, and understanding the heliosphere's shielding behavior is critical to planning long-duration missions safely. It is important to be clear about what the heliosphere does not do. It does not shield the inner solar system from every kind of radiation. It does nothing at all against sunlight itself, or against radiation coming from the sun, which is a very different problem. It does not block all cosmic rays, only a fraction of them. It does not protect Earth from solar flares or coronal mass ejections, which originate inside the heliosphere and are in fact driven outward through the heliosphere by the same processes we have been discussing. And importantly, the heliosphere is only one of several layers of protection that make the surface of Earth habitable. Around Earth, we have our own magnetic field, generated by the motion of molten metal in our planet's core. This magnetic field forms what is called the magnetosphere, a bubble of magnetic influence surrounding our planet that deflects charged particles, blocks much of the solar wind from directly reaching our atmosphere, and helps preserve the atmosphere itself from being stripped away over billions of years. Above that, we have our atmosphere, which absorbs and scatters ultraviolet radiation, X-rays, and many cosmic ray secondaries before they can reach the ground. And around all of it, at a vastly larger scale, is the heliosphere doing its own partial job of shielding. Each of these layers matters. Each of them does something different. None of them is complete on its own. And no honest description of the environment around Earth should claim that the heliosphere alone protects us from the galaxy. It plays a role. It's not the whole story. Now, one of the most interesting recent developments in heliophysics has been the recognition that our sun is not unique in producing this kind of structure. Other stars throughout the galaxy produce similar bubbles around themselves through the same fundamental process. Every star that has any kind of stellar wind, and that turns out to be most stars, creates its own version of the heliosphere in the space around it. These structures have a general name. They are called astrospheres, and studying them has become a way for us to place our own home in a wider stellar context. Astrospheres come in many sizes and shapes. Some stars have much more powerful stellar winds than the Sun. Massive, hot young stars can produce winds thousands of times more energetic than our suns, blasting huge cavities into the surrounding interstellar medium. Other stars produce much weaker winds, and their astrospheres are correspondingly smaller and less impressive. The shape of an astrosphere depends on the star's wind properties, the surrounding interstellar environment, and the star's motion relative to that environment, just as it does for our own sun. Astronomers have observed astrospheres around a number of nearby stars using various techniques. Ultraviolet observations from telescopes like the Hubble Space Telescope have revealed the signatures of these structures around stars like Proxima Centauri, the nearest star to the Sun. Comparing our heliosphere to these other astrospheres has helped scientists refine their understanding of how such structures form and evolve. And it has confirmed that the heliosphere is not unusual. It is a normal, typical feature of a star that produces a stellar wind and moves through an interstellar environment. Every star with these properties has its own version of it. The galaxy is filled with plasma bubbles, carved out by stars, all of them slowly drifting through the interstellar medium, all of them creating their own local environments. This raises an interesting question. Does the presence of an astrosphere matter for the possibility of life on a planet? The honest answer is that we do not fully know. Life on Earth clearly evolved inside the Sun's heliosphere, and the partial cosmic ray shielding it provides is one factor among many in the environmental history of our planet. But whether life could evolve on a planet orbiting a star with a very different astrosphere, one that is much smaller or shaped very differently, or that surrounds a star producing much more or much less stellar wind, is not something we can say with certainty. Some scientists have argued that astrospheres are important for habitability. Others have argued that other factors like planetary magnetic fields and atmospheres are far more important. The truth probably lies somewhere in between, and it likely varies significantly from one star system to another. What we can say is that the concept of an astrosphere places our situation in perspective. Our home is not special because it has a heliosphere. It has one because our sun produces a solar wind and moves through interstellar space, just like most stars in the galaxy. But the specific properties of our heliosphere, its size, its shape, its shielding behavior, its response to solar activity, are all specific to our star and our local environment. Another star would have a different astrosphere. Another planet inside a different astrosphere would experience a different environment. Understanding these differences is one of the frontiers of comparative stellar astronomy. Now, if we zoom out further in time, the story gets even more remarkable. The sun's motion through the galaxy is not just a matter of drifting through the local interstellar cloud today. Over its 4.5 billion year history, the sun has traveled enormous distances through the Milky Way, passing through many different galactic environments, encountering many different kinds of interstellar material. And every one of those environments would have shaped the heliosphere differently. We already mentioned that the sun is currently passing through the local interstellar cloud, having entered it somewhere between 40,000 and 150,000 years ago. Before that, our star was traversing a much larger region called the local bubble, an area of relatively low-density interstellar gas that was carved out by supernova explosions from massive stars that lived and died in our region of the galaxy several million years ago. The local bubble is about 300 light-years across, which sounds tiny on galactic scales, but is actually a substantial region, and inside it, the interstellar medium is thinner and more rarefied than in many other parts of the Milky Way. This means that during the sun's passage through the local bubble, the heliosphere may have been able to expand relatively easily, reaching out to somewhat greater distances than it does today, since there was less external pressure pushing back. But at various times in the deep past, the sun would have encountered denser interstellar regions. Dense molecular clouds, remnants of ancient star-forming activity, and various clumps of interstellar material would have passed through our neighborhood, or the sun would have passed through them. And in those denser environments, the heliosphere would have been more compressed. The termination shock would have moved inward. The heliopause would have been closer to the sun. In extreme cases, if the sun ever encountered a truly dense interstellar cloud, the heliosphere could theoretically be compressed so much that its boundary would move inside the orbit of the outer planets, or even the inner planets. Whether this has ever actually happened during Earth's history is a matter of ongoing research. Some scientists have argued that certain features of Earth's geological or biological history might correspond to episodes of unusual interstellar compression. Others argue that the sun's current path has not encountered anything sufficiently dramatic. This is speculative territory, and it should be treated as speculative rather than settled. What is not speculative is the general principle. The heliosphere is not fixed on cosmic timescales any more than it is fixed on human timescales. It has changed, sometimes dramatically, over the sun's long history, and it will continue to change in the future. In another 100,000 years, the sun will be somewhere else in its journey around the galaxy, encountering different material, producing a different shaped heliosphere. In another 1,000,000 years, that difference will be even greater. In another 1,000,000,000 years, we would barely recognize the environment our star will be traveling through, though the sun itself will still be shining and still producing its solar wind, still carving out its own plasma bubble in whatever material it happens to be passing through. Which brings us back one more time to where all of this started. The heliosphere is the shape our sun makes in the galaxy. It is the region carved out by the continuous outflow of solar wind, held in balance against the surrounding interstellar medium, structured by the sun's magnetic field, and organized by the sun's motion through the galactic environment. Everything about it, its size, its boundaries, its rhythms, its response to solar activity, its interactions with the interstellar environment, its extended downstream structure, is a consequence of that simple ongoing process. A star blowing outward, the galaxy pushing back, and in between, an enormous, invisible, ever-changing environment inside which we live our entire lives. There are still many things we do not know. We do not know the exact three-dimensional shape of the heliosphere with certainty. We do not know the true length of the heliotail. We do not know whether the shape is better described as classically comet-like, as a more compact, rounded structure, or as some combination of both that varies with the solar cycle. We do not know the full explanation for the IBEX Ribbon, and different theoretical proposals for its origin remain in competition. We do not know exactly how the sun's magnetic field is organized in the far downstream regions, or how magnetic reconnection processes there affect the mixing between solar and interstellar plasma. We do not know how much the heliosphere may have changed during past encounters with denser interstellar clouds, or how it will change during future ones. Future missions may help answer some of these questions. Astronomers have proposed several concepts for a dedicated interstellar probe that would travel outward through the heliosphere, past the boundaries the Voyagers crossed, and further into the local interstellar medium, taking measurements at a much faster rate and with more advanced instruments than anything currently in operation. Such a mission would not be quick. Launching one would still mean waiting decades for the results, but it could vastly improve our understanding of the outer heliosphere and the surrounding galactic environment. There are also proposed next-generation missions to observe the outer heliosphere remotely, mapping energetic neutral atoms with higher resolution than IBEX has achieved, testing between competing shape models, and refining our picture of the boundary interactions. Whatever those missions find, whatever they reveal, they will not change the fundamental picture we have built here tonight. The planets do not travel through the galaxy alone. They ride inside an enormous invisible structure carved out by the sun. This structure is not solid. It is not permanent. It is not the same on every side. It is compressed on the side facing the sun's motion through the local interstellar medium. It is extended, in ways we are still working out, on the trailing side. It breathes with the 11-year rhythm of solar activity. It shifts with the slower rhythm of the sun's motion through different galactic environments. And it holds within itself every human being who has ever lived. Every civilization that has ever risen. Every act of art or science or discovery or love that our species has ever produced. Every star you have ever seen with your naked eye is doing the same fundamental thing that our sun is doing. Those distant points of light are each surrounded by their own astrospheres, their own plasma bubbles carved out by their own stellar winds, drifting through the same interstellar galaxy that our sun drifts through. Somewhere among them, there are almost certainly other systems where similar physics plays out, where similar boundaries mark the transitions between one star's influence and the wider galactic environment. Some of those systems may host planets. Some of those planets may host life. And if that life ever develops the ability to look outward and understand its own place in the cosmos, one of the first things it will discover, just as we have discovered, is that it does not simply live on a planet orbiting a star. It lives inside an enormous, invisible, breathing structure that its star has carved out of the surrounding galaxy. The Heliosphere is our home. It is bigger than most of us ever realize. It is stranger than most illustrations manage to convey. It is still being explored, still being mapped, still being debated at the highest levels of professional science, and it is one of the most beautiful examples anywhere in astronomy of how the universe uses simple, continuous processes: a star emitting a wind, a galaxy pushing back over enormous stretches of time to create structures so complex and so vast that we can barely see the edges of them from inside. Every atom of every human being, every breath you have ever taken, every moment of consciousness you have ever experienced, all of it has happened inside the same enormous plasma bubble that trails behind our moving star. That is not a small fact. That is the shape of home. And now that you know it is out there, you will never be able to look at the night sky in quite the same way again. Let us take a moment and try to feel the actual scale of what we have been describing. Not the numbers, not the astronomical units, but the physical progression from one end of the solar system to the other. Begin with the sun, that ball of plasma about 865,000 miles across. Set that as your starting point. Now move outward. In about 3 minutes at the speed of light, you would reach the orbit of Mercury. In 8 minutes, you would reach Earth. In roughly 43 minutes, you would reach Jupiter. In about 4 hours, you would reach Neptune's orbit, the outer edge of the classical planetary region. That entire journey, from the sun's surface all the way to Neptune, takes light a matter of hours. And for most of human history, this was as much of the solar system as anyone imagined existed. Keep going outward. Past Neptune, past Pluto, past the icy bodies of the Kuiper Belt, past the region where the last known dwarf planets orbit in their slow, dark loops. Somewhere between 10 and 12 hours out at the speed of light, you begin to enter the region where the termination shock lies, about 14 to 16 hours at light speed, depending on which direction you are moving. Continue outward, and you enter the heliosheath, that enormous turbulent zone of shocked solar plasma. It takes light between 16 and 17 hours to cross the heliosheath in the direction Voyager 1 travelled, and then, finally, you reach the heliopause, roughly 120 astronomical units out, 16 to 17 light hours from the sun on the upstream side. To grasp the ratio here, consider this. Light takes about 8 minutes to reach Earth. Light takes about 16 hours to reach the heliopause. That is a ratio of roughly 120 to 1. The heliosphere is 120 times wider than the Earth-Sun distance on its compressed upstream side, and it is likely much wider in other directions. Downstream, in the direction the heliotail extends, the effective size may be several times larger. Sideways, somewhere in between, the heliosphere is not just larger than the planetary region, it absolutely dwarfs it. If Earth's orbit were a coin sitting on your desk, the heliosphere would extend across your entire room, and the planetary region would be a tight cluster around the center of the coin. But even the heliosphere is not the true edge of the solar system, because beyond it, extending for enormous distances further, sits the vast reservoir of icy bodies called the Oort Cloud. If the outer edge of the Oort Cloud is at 100,000 astronomical units, and if the heliopause is at about 120 astronomical units, then the Oort Cloud extends outward for roughly 1,000 times as far as the heliosphere itself does. If Earth's orbit is a coin, and the heliosphere is your room, then the Oort Cloud is your entire city. And the sun's gravity, that patient, silent, invisible force, still holds those distant icy bodies in orbit. They are still part of the solar system in the gravitational sense, still bound to our star, still, technically, at home, even though they sit in what most heliophysicists would classify as interstellar space in the plasma sense. This is the strange truth of our situation. The heliosphere is our plasma home. The Oort Cloud is our gravitational home. And these two homes disagree about their boundaries by a factor of 1,000. When we ask where the solar system ends, we are really asking which home we mean. Let us pause for a moment and think about what the space between the planets is actually like, because this is one of the most misunderstood aspects of the solar system. When people picture interplanetary space, they usually imagine emptiness. A vast, dark, silent vacuum stretching between the planets, with nothing in it but the occasional passing spacecraft or drifting asteroid. But that picture is wrong. The space between the planets is not empty. It is filled with the solar wind. It is threaded with the sun's magnetic field. It is patrolled by energetic particles from solar flares, by cosmic rays that have penetrated from the wider galaxy, by dust grains from ancient comet passages, by neutral atoms drifting in from the interstellar medium. Every cubic mile of space between here and Neptune contains a mixture of all of these populations, invisible to the naked eye but very real and very active, and very much a part of the environment that every planet exists inside. The environment beyond the heliopause differs in one critical way from the space inside our plasma bubble. The magnetic field points in a completely different direction. Inside the heliosphere, the field is organized around the sun, wound into the Parker spiral by our star's rotation. Outside, the field belongs to the galaxy itself, oriented by processes that operated billions of years ago in ancient supernova explosions and the slow rotation of the Milky Way. When Voyager 1 crossed the heliopause, one of the most striking changes its instruments recorded was in the direction of the magnetic field. It rotated, not by a little, but by a significant angle, marking the transition from solar magnetism to galactic magnetism. This shift is one of the clearest signatures that the spacecraft had truly left the sun's magnetic domain and entered the wider interstellar environment. The plasma density also increased. The particle populations changed character, and the cosmic ray intensity jumped. But the magnetic field rotation was the smoking gun that scientists had been waiting decades to observe. Now, the heliosphere sets the environment for every planet in the solar system, and each planet responds to that environment in its own way, depending on its own particular properties. Consider what happens at Mercury. Mercury sits inside the heliosphere, closer to the Sun than any other planet, exposed to the full brunt of the solar wind at its most intense. Mercury has a weak magnetic field, generated by processes in its core that scientists still do not fully understand, but that field is only about 1% as strong as Earth's. So Mercury cannot deflect much of the solar wind. The wind slams into Mercury's surface directly in many places, and it interacts with Mercury's tenuous atmosphere in ways that make that atmosphere itself a product of solar wind bombardment. Every atom in Mercury's thin atmosphere is either freshly liberated from the surface by particle impacts, or on its way to being lost to space by the very same processes. The Heliosphere writes Mercury's atmospheric story every single day. Venus tells a different story. Venus has no significant magnetic field of its own, but it has an enormous atmosphere, dense enough to crush spacecraft in seconds. That atmosphere provides its own defense against solar wind, in the form of what scientists call an induced magnetosphere, generated by currents in the upper atmosphere as the solar wind flows past. Even so, the solar wind constantly strips atoms and molecules from the outer edges of Venus's atmosphere, contributing over billions of years to the loss of hydrogen and other light species. If Venus ever had oceans in the deep past, and there are hints that it might have, the solar wind's steady erosion of the atmosphere may be part of the reason those oceans are gone. Mars offers perhaps the most poignant example. Mars is a world that once had liquid water flowing across its surface, rivers, lakes, possibly even oceans. Mars had, in the ancient past, a much thicker atmosphere than it does today. And Mars, we believe, once had a strong magnetic field. But then, somewhere in the deep past, Mars's magnetic field collapsed. The molten interior that had been generating that field cooled and solidified. And without a magnetic shield, Mars became exposed to the solar wind in a way that Earth never has been. Over hundreds of millions of years, the solar wind stripped Mars's atmosphere away, piece by piece, molecule by molecule. Until the thick air was gone, the water could no longer stay liquid, and Mars became the cold, dry, dusty world we know today. The heliosphere did not just fill the space around Mars, it transformed Mars. It participated in one of the most dramatic climate transitions in the history of any planet we know. Earth, by contrast, has thrived inside the heliosphere in part because of the combination of protections we discussed earlier. Our magnetic field deflects most of the direct solar wind. Our atmosphere absorbs most of the remaining radiation, and the heliosphere itself provides a partial shield against galactic cosmic rays. All three layers work together. Take away any one of them, and Earth would be a very different and probably much less habitable world. Even the outer planets have their own dramatic interactions with the heliosphere. Jupiter, in particular, has a magnetosphere so enormous that if you could see it in the sky, it would appear larger than the full moon. Jupiter's magnetic field is thousands of times stronger than Earth's, and it carves out a bubble in the solar wind that is one of the largest magnetic structures in the entire solar system, other than the heliosphere itself. Inside that Jovian magnetosphere, particles get accelerated to enormous energies, creating radiation environments that would be lethal to any unshielded astronaut, and difficult even for spacecraft to survive. The heliosphere sets the outer context, but Jupiter creates its own weather within that context, and its magnetosphere itself is a kind of miniature version of what the Sun does at a vastly larger scale. Saturn, Uranus, and Neptune each have their own magnetospheres too, each responding to the solar wind in their own ways, each shaping the space around themselves inside the larger context of the heliosphere. Every planet is, in effect, a nested bubble inside the bigger bubble that the Sun creates. The heliosphere is the largest of these nested structures, but it is not alone. It is the outer envelope of a whole hierarchy of magnetic environments, extending down to the surface of individual planets. Now think about the Voyagers again for a moment. Voyager 1 and Voyager 2 launched in 1977. That was almost 50 years ago. The Voyagers were designed as a 2-planet mission, originally to fly past Jupiter and Saturn. That was the primary goal. Everything they have done since then, the extended tour of Uranus and Neptune, the long journey across the Helios Heath, the historic crossings of the heliopause, all of it was possible only because the spacecraft survived far longer than anyone dared to hope. Both Voyagers are still returning data today, nearly 5 decades after launch, from distances greater than any human-made object has ever reached. Their signals now take almost a full day to reach Earth at the speed of light. Their power sources, radioactive plutonium slowly decaying inside their generators, are running out. Within the next decade, both spacecraft will probably fall silent, unable to power their instruments any longer, but they will not stop moving. Their momentum will carry them outward forever, drifting through interstellar space for millions of years, long after every human being alive today is gone, long after our civilizations have transformed or ended. Voyager 1 will pass within about 1.5 light years of a star, called Gliese 445, in roughly 40,000 years. Voyager 2 will pass a different star at a similar time. Neither spacecraft will ever return. Neither will ever be recovered. They are humanity's most distant ambassadors, carrying gold-plated records of our music and our voices, drifting silently outward through the wake of our star, out into the vast, cold darkness between the suns. Think about the timescales involved here. Interstellar space is so empty, so cold, so utterly devoid of anything that could erode a spacecraft, that the Voyagers will remain almost perfectly preserved for extraordinary spans of time. In 1 million years, they will still exist, still recognizably spacecraft, still carrying their instruments, their antennas, their golden records. In 1 billion years, when the sun has begun swelling into a red giant and Earth's oceans have long since boiled away, the Voyagers will still be drifting through the galaxy, essentially unchanged. They may well be the longest-lasting artifacts our civilization ever produces. Everything else we build will crumble. The Voyagers, silent and forgotten, will endure. There's something profound about that thought. When the last spacecraft signal from either Voyager finally goes silent, humanity's direct measurements of the outer heliosphere and interstellar space will end. We will have no more real-time data from those regions until some future mission is sent. It could be years, decades, perhaps a century before we have another spacecraft measuring conditions in the outer Helios Heath or the local interstellar medium. Everything we know from that region for a very long time to come will be based on the measurements the Voyagers took during their brief active years. Those measurements are irreplaceable, and the humans who designed and built those spacecraft, most of them born before World War II, will have provided the only in-place data we have from beyond the heliosphere for perhaps another generation or more. Now, inside all of this enormous structure, there is a cast of characters we have not yet properly introduced. Not planets, not moons, not comets, but populations of particles with peculiar properties that only make sense in the context of the heliosphere itself. Let us meet a few of them because they add depth to the picture and they show how much richness there is inside this vast plasma environment. The first of these are called pickup ions. To understand what they are, you have to remember that the interstellar medium is not empty. It contains neutral atoms, mostly hydrogen and helium, that drift lazily through space at the modest thermal speeds characteristic of very thin gas. Because these atoms are electrically neutral, they do not care about magnetic fields. The heliopause, the great plasma boundary, means nothing to them. They drift straight through it, into the outer heliosphere, into the Helios heath, into the inner solar system, without being deflected at all. Some of them make it all the way to the vicinity of Earth. If you could tag one of these interstellar hydrogen atoms and follow it, you would watch it float in through the heliopause, past the outer boundary, gently making its way toward the inner solar system, unaware of the plasma domain it has entered. But at some point, that neutral atom encounters something, either an ultraviolet photon from the sun, or an energetic charged particle in the solar wind. And in that encounter, it loses its electron. Suddenly, it is no longer neutral. It is a positively charged ion sitting inside the solar wind plasma. And the moment that happens, the magnetic field carried by the solar wind grabs hold of it. The ion, which was drifting slowly, now finds itself embedded in a plasma flowing outward at hundreds of miles per second. It gets swept along, joining the flow, becoming part of the solar wind. It has, in effect, been picked up by the wind. And that is why these particles are called pickup ions. Pickup ions matter because they are a hidden population inside the heliosphere. They start out as interstellar visitors, they end up as accelerated solar wind travelers. They add mass to the solar wind, they change its momentum, and they alter its behavior in ways that matter for the whole outer heliosphere. And there is more to their story. Because as pickup ions travel outward through the solar wind, they can be accelerated further by the termination shock. When they hit that shock, some of them gain enormous amounts of energy, becoming a specific kind of energetic particle that scientists have long been fascinated by. These are called anomalous cosmic rays. Anomalous cosmic rays are, in a sense, immigrant cosmic rays. They were not born in some distant supernova. They started life as neutral atoms in the local interstellar medium, drifted into the heliosphere, got ionized somewhere in the inner solar system, got picked up by the solar wind, got carried outward, and got accelerated by the termination shock, two energies that make them behave a lot like galactic cosmic rays. They have a different composition from normal galactic cosmic rays, which is how astronomers first realized they were a distinct population. They contain a lot more helium and oxygen and nitrogen than you would expect from a normal galactic cosmic ray sample. And their energy spectrum is different too. These properties are the telltale fingerprints of their unusual origin. They are cosmic rays made in our own backyard, in a way that no other cosmic rays are. Studying anomalous cosmic rays has given us one of the most powerful indirect ways of understanding what happens at the termination shock. Because we can measure their energies, their compositions, and their arrival directions at Earth. And from those measurements, we can reconstruct information about the acceleration process out at the shock front. Voyager 1 and Voyager 2, in fact, measured anomalous cosmic rays directly as they crossed the termination shock. And what they found was surprising. The shock was not accelerating these particles as efficiently as everyone had expected. There was something more complicated going on. some aspect of the acceleration process that scientists are still trying to fully understand. It is another reminder that the outer heliosphere, even after decades of study, still holds mysteries. There's another kind of event that shapes the entire heliosphere from the inside, and this one is much more familiar to most people. Solar flares and coronal mass ejections. These are the explosive events that occur near the sun's surface, driven by the sudden release of energy stored in twisted magnetic field structures. A large coronal mass ejection can hurl billions of tons of solar plasma outward at speeds ranging from a few hundred to several thousand miles per second. And that ejected material, that enormous plasma cloud, does not just affect Earth. It propagates outward through the entire heliosphere. It travels for weeks or months, expanding as it goes, eventually reaching the outer regions where the termination shock and heliosheath sit. When a large coronal mass ejection reaches the outer heliosphere, it can create a disturbance in the boundary regions. Sometimes it can push the termination shock outward temporarily. Sometimes it drives a shock wave of its own that plows through the heliosheath. And sometimes, when multiple coronal mass ejections have propagated outward in sequence, they can merge together into enormous plasma structures that scientists call merged interaction regions. These merged interaction regions can dominate the state of the outer heliosphere for months at a time, altering the passage of galactic cosmic rays through the boundary, changing the pressure balance at the heliopause, and effectively broadcasting the mood of the sun to the very edge of its plasma domain. This is one of the reasons the outer heliosphere is dynamic on many timescales at once. The 11-year solar cycle sets the slow rhythm. Individual solar events superimpose faster variations on top of that rhythm, and propagating structures from those events travel outward for months. So at any given time, the outer heliosphere is responding to a mixture of everything the sun has done in the past several months to years. It is, in a sense, always hearing echoes of its own past. Now, at the same time as all this internal activity, we should consider what missions are being planned or currently flying to continue mapping the heliosphere. IBEX has been observing the sky for over 15 years, and it continues to return data. But NASA has developed a successor mission called IMAP, short for the Interstellar Mapping and Acceleration Probe. IMAP will build on what IBEX started, mapping energetic neutral atoms with much better sensitivity and resolution, while also carrying additional instruments to study the solar wind and the local interstellar environment. Data from IMAP is expected to sharpen our picture of the outer heliosphere considerably. It may finally help settle some of the longest-running arguments about the exact shape of the heliosphere, the true nature of the IBEX Ribbon, and the fine-scale structure of the heliopause and beyond. There are also more ambitious concepts under discussion. Some heliophysicists have proposed missions to send a probe far beyond the heliopause, hundreds of astronomical units into interstellar space, with instruments designed specifically for that environment. Such a probe would take decades to reach its target, and decades more to complete its primary mission, but it would provide direct, in-place measurements of interstellar plasma over a large range of distances, giving us the kind of data that no all-sky remote observation can match. Whether such a mission will actually fly in the coming decades depends on funding, technology, and priorities. But the scientific case is strong. Every decade we go without such a mission is a decade in which our knowledge of the outer heliosphere and the surrounding interstellar environment remains dependent on just a handful of aging spacecraft and remote observations. Now, let us return one more time to the wider context, to other stars, to other systems, to the fact that the heliosphere is one example of a more general phenomenon that occurs throughout the galaxy. We touched on astrospheres earlier, but it is worth being specific about a few examples because the variety turns out to be tremendous. Take the star Alpha Centauri A, which is broadly similar to our Sun in mass, temperature, and age. It sits about 4 light years away, closer than any other star system to us. Alpha Centauri A produces a stellar wind roughly comparable to our Sun ES, and it carves out an astrosphere in the surrounding interstellar medium that is thought to be similar in general character to our heliosphere. The shape and details differ because the local interstellar environment near Alpha Centauri is not exactly the same as ours, but the basic architecture, a stellar wind bubble carved out of the surrounding galaxy, is recognizable. A hypothetical observer at Alpha Centauri A would see its own version of a termination shock, a sheath region, a boundary with the interstellar medium, and probably a downstream extension shaped by that star's motion through the local galaxy. Now compare that to a completely different kind of star. Consider a young, massive star, one that is many times more massive than the Sun, and much hotter and brighter. Such a star can produce a stellar wind that is thousands of times more powerful than our Sun's, sometimes even more. The astrosphere around such a star can be enormous, extending for tens or hundreds of light years in some cases, hollowing out huge cavities in the surrounding interstellar medium and even influencing the formation of new stars nearby. These are the kinds of astrospheres that are visible directly in optical and infrared images. You can literally see them in some photographs of nearby star-forming regions, glowing shells and cavities carved by the winds of hot young stars. At the other extreme, consider a very small, cool star, a red dwarf with much less than 1/10 of the Sun's mass. Such a star produces a much weaker stellar wind, and its astrosphere is correspondingly smaller. In some cases, the astrosphere around a red dwarf might be so compact that it barely extends beyond the star's own planetary system, if it has one. This has interesting implications for the possibility of life around red dwarfs, which are the most common type of star in the galaxy. If the astrosphere is small, and if the planets orbit close to the star, then those planets may not benefit from the kind of partial cosmic ray shielding that Earth enjoys from the heliosphere. They might sit closer to the boundary between stellar and interstellar plasma, exposed to more radiation from outside and less protected than we are. There is another complication for red dwarf planets. These stars are often magnetically active, producing frequent flares that are, relative to the star's overall brightness, extremely powerful. So even as the astrosphere is smaller and less protective, the star itself is producing more intense outbursts. Whether the balance of these factors makes life more or less likely on planets around red dwarfs is a topic of ongoing research. What it clearly illustrates is that not all astrospheres are alike, and the specific properties of a star and its environment matter enormously for the local space weather that any planet inside experiences. We can also consider stars that are similar to the Sun, but are moving much faster through the interstellar medium. The relative velocity between a star and its surrounding gas has a big effect on the shape of its astrosphere. A star moving quickly through dense gas produces a much more sharply compressed upstream boundary, sometimes accompanied by a genuine, unambiguous bow shock, unlike the more marginal situation for our own sun. And in some cases, telescopes have imaged such bow shocks directly around stars moving through relatively dense interstellar regions. These images give us direct visual examples of what astrospheres can look like under more extreme conditions than our own, and they help calibrate our understanding of the physics. All of this comparative work matters because it lets us place our own situation in context. Our heliosphere is not the biggest astrosphere in the galaxy, not by a long stretch, but it is also not the smallest. Our sun is not the most active star, but not the quietest either. Our local interstellar environment, the local interstellar cloud we are currently drifting through, is not the densest cosmic weather we could encounter, but it is not the emptiest either. In every dimension, we are somewhere in the middle. Our situation is characteristic of a fairly typical, middle-aged, medium-mass star drifting through a moderately calm neighborhood of the galactic environment. Which means the story of our heliosphere is, in a sense, the story of a very common kind of stellar home. There are almost certainly many, many similar homes scattered across the Milky Way, each one carving its own bubble, each one hosting its own planetary system, each one experiencing its own weather. And this brings us to the final, most sweeping realization. The point that ties everything we have talked about together into a single, coherent picture of what it means to live in the environment surrounding a star. Our solar system is not a static collection of planets orbiting an isolated point of light in the darkness of space. It is a moving, breathing, dynamic system embedded in an even larger moving, breathing dynamic structure. The sun is exhaling constantly, throwing out plasma and magnetic field lines that fill the space around it. That exhalation carves out a region of dominance, the heliosphere, that stretches for well over 100 astronomical units in every direction. And as our whole moving solar system travels through the surrounding galaxy, that plasma region is being compressed on its leading side, stretched or channeled on its trailing side, breathing with the 11-year rhythm of the sun's magnetic cycle, responding to the encounters with different galactic environments along our star's long orbital journey around the Milky Way. Everything we know, every planet, every human being, every civilization, every act of art or love or discovery has happened inside this vast, invisible, ever-changing structure. And most of us have never even thought about it. That is the true scale of the heliosphere. Not just a bubble around the sun, but our actual home in the galaxy. The space that surrounds every planet in the solar system is not empty space. It is filled with our sun's plasma. It is threaded with our sun's magnetic field. It is patrolled by particles our sun has released, energized by shocks our sun has driven, and shielded, imperfectly, partially, but genuinely, from the harsher radiation of the wider galaxy by the very presence of everything our sun has been giving off for the last 4.5 billion years. The heliosphere is not something that happens to the solar system. It is, in a very real sense, what the solar system is, at the largest scale. And the story is not finished. We continue to explore this environment. New spacecraft, new observations, new models will continue to refine our picture over the coming decades. The exact shape of the heliotail may become clearer with IMAP data. The origin of the IBEX Ribbon may finally be settled. The three-dimensional geometry of the heliosphere may be mapped in unprecedented detail. Or new mysteries may emerge, new features may be discovered, and the picture may become even richer and stranger than we currently imagine. That is how frontier science works. Every answer opens new questions. Every measurement suggests new experiments. And every generation of astronomers hands off to the next generation a set of problems that are, in many ways, more sophisticated and more subtle than the ones they inherited. But whatever we discover in the future, the fundamental picture is likely to hold. We live inside a plasma bubble carved out by our star. That bubble is enormous. It is not spherical. It is not static. It moves. It breathes. It has an upstream side that faces the direction our sun is traveling through the galaxy. And it has a downstream side that trails behind us, extending outward in ways we are still working to understand. It shields us, partially, from the wider radiation of the galaxy. It sets the stage for the space weather that affects every planet, every satellite, every astronaut, every technological system that reaches beyond the immediate vicinity of Earth. And it is only one example of a general phenomenon, the astrosphere, that occurs throughout the galaxy around countless other stars. The next time you go outside at night and look up at the sky, remember that you are not just standing on a planet. You are standing on a planet embedded inside a vast, invisible, moving, breathing structure that stretches for many billions of miles in every direction. You are looking outward through that structure at the light of other stars, each of which has its own version of the same kind of structure around it. You are participating in a phenomenon that has been unfolding for billions of years and will continue to unfold for billions of years more, long after every human being alive today is gone, long after our civilizations have transformed into something we cannot even imagine, long after the sun itself has changed in ways that will eventually reshape everything we now know. The heliosphere will still be there. Some version of it will still be carving space around our star for as long as that star continues to shine. And every atom, every particle, every wisp of plasma inside it will continue to flow outward, ever outward, on its long, slow journey to the boundary with the wider galaxy beyond. That is the world we live in. That is the scale of home. That is the true, invisible architecture of the solar system, hidden in plain sight all along, waiting for anyone patient enough to look outward and see it. And now that you have seen it, you carry that picture with you. The next sunset you watch, the next clear night sky you gaze at, the next time you feel the wind on your face or the sunlight on your skin, remember that the source of all of it, the sun itself, is doing something far greater than just shining. It is carving the space we live in. And that space, that vast, silent, invisible heliosphere, is our home in the galaxy. Good night, and may you never look at the sun the same way again.